Hi, this is Kenny, and here is Zoe. We would like to present our finite element analysis of a three-wheel real suspension. The objective here is to design a real suspension for a single real-wheel three-wheel car like the three-wheel solar car designed by MSU Solar Car team. The suspension is designed to be connected with damper, motor, and body chassis. For current suspension of a MSU Solar Car team, it is a L-shaped suspension with aluminum 7000, which is hard to weld and mill. The safety factor of current suspension is 2.5 with twice the weight of a whole car. The new design of a suspension is desired to be a simple structure with a material that is easy to weld and mill. Also, the safety factor of a new suspension is expected to reach 5. These two figures are our first overview design that produced using top OPT 3D design. The ratio between the dimensions is set to be 3 to 1 to 1. In the figure on the right, we can clearly see that the edge of the lower left was constrained to be fixed in all directions, and there is where the chassis will be connected to. In the figure on the left, a force of 3,000 pounds was applied at the upper right corner to simulate the force gained by the damper. The left constraint is fixed at the lower right corner where the motor and wheel will be connected. The material we use in this design is ASTM A36 steel, using the dimension ratio introduced in the last slide. The dimension is 15 inches in length, 5 inches in width, and 5 inches in height. The yield strength, Poisson ratio, and density of this kind of steel are presented as following. Using the structure concept produced by Top OPT 3D, here is our first design using NX. The mesh size we used throughout the analysis are all 0.2 inch. The maximum displacement we experienced on our first design is about 1.5 to the 10th power of negative 3 inch. The red part of the design is where the maximum deflection occurs. The deflection runs throughout the structure instead of places where the constraints were at. The maximum elemental stress is about 9,200 pounds per square inch, and it locates near the lower right corner where the fixed constraint was. Most stresses appear only at the joint. The maximum nodal stress is about 19,000 pounds per square inch. The maximum stress is located at the same location as the maximum elemental stress. After our first iteration, here is our second design. Instead of extra joint, we use straight beam to connect, and let's see the result. Compared to our first design, the maximum displacement is reduced to 7.5 to the 10th power of negative 4 inch, which is about half of the displacement of our first design. The maximum elemental stress is about 7,300 pounds per square inch near the lower right corner. The maximum nodal stress is about 15,000 pounds per square inch located at the lower right corner.
Compared with the first two designs, the second one is the optimal one because it has a smaller displacement and smaller nodal and elemental stress. So we changed the lower right corner to be a circular to connect with the motor of the wheels. After the simulation, we can see the maximum displacement of the structure is still located at the top corner, which is almost zero. Although it is almost zero, but it is still like half about the second design. For the elemental stress simulation, the result is about like 4,300 psi, which the maximum stress is located at the top corner. For the nodal stress simulation, the value is about 7,200 psi, and the location is still the same with the previous one. From the first design to the third design, the maximum stress for nodal and elemental and also for the maximum displacement, they are all decreasing. The safety factor of the first one is 3.9 to the safety factor for the second one is 4.94. The safety factor of the third one is 8.44. Overall, maximum displacements are extremely small for all three designs. Maximum stress for elemental and nodal are smaller than the yield strength of ASTM A36 steel. The weight is approximately 36.1 pounds. For the future improvement, we want to reduce the weight so we can use hollow tube or use different materials such as aluminum or reduce the diameter of the tube. We can also change the different structure to adjust the shape of structure to avoid touching the rear wheel, or change the parts that connect with the motor to fit different types of motor, or make it able to install the brake calipers. Okay, so this is our final design. Thank you. Any questions?